Hello? Hi, Alex. Can you hear me? Hello? No, I can't hear you.
I'll go ahead and start now then. So for this week's tutorial, I'll be going over RNN and LSTM, the primary backbone for NLP tasks when it comes to deep learning. As well as, so for today's agenda, again, as I mentioned, I'll be covering RNN and LSTM. However, due to demand from prior last week's session, I'll also be covering CNN at the beginning, looking at how CNN can be used for NLP task. From my experience, CNN type of models for NLP task is in most cases it's comparable to RNN or LSTM. It's only in some instances where I've seen better performance with CNN in NLP task. However, those instances has primarily been in NLP tasks, specifically for classifications, as we're doing now. However, it is primarily in cases where the classification itself is very straightforward as well. There is, it's the data set's very clean and discernible when you're for the specific classification task you're doing, as well as the complexity of the classification task isn't as complex. Those are the instances where I've seen CNN perform slightly better than RNN and LSTM. However, I think a lot of people are familiar with CNN, so that's where the popularity comes in. So I'll be more than happy to kind of go over it right now. So for this week's learning objective, again, we're going to provide an understanding of how CNN can be applied to NLP tasks. So CNN is primarily for image processing. However, there is a technique such that the architecture can be used for NLP. We'll look at we'll provide fundamental knowledge for RNN and Lstm, be able to identify limitations for both RNN and Lstm, as well as implement and design RNN with pre-trained embeddings. So straight to it, CNN. For anybody that's not familiar with CNN, on images, we'll do a quick recap here. So CNN utilizes kernels to understand the features of the input space. So in this example right here, the input image right now is the MNIST data set. It's very popular data sets to begin with when working with CNN. It's just handwritten digits from 0 to 9. And the objective is to classify the handwritten digit as the actual numerical value from 0 to 9. So the way CNN works is you have this square kernel. So in this case, this kernel is a 2x2, and it overlays over the image, and it performs convolution. That's where the name comes from. So it performs convolution to generate a feature map. So what the convolution is in terms of the CNN, it's just a pairwise multiplication and summations of the pixels with the overlapping. So in this case, I'm not sure. Eunice, can you verify for me if you are able to see my cursor?
Yes, we can.
Yes, okay. So the cursor, where I have over my cursor, so in this specific instance, this kernel will do a multiplication of this weight within this kernel location with the pixel that's overlaying it, multiply this pixel with the weights of this within this location, and so on and so forth, and then they'll perform the summation of those multiplications, generating one unit value for this whole region. And what CNN does afterwards is it slides over to the next location. So in this case, the stride is of 2. So it's moving 2 pixels down and performing the same convolution operation, performing pairwise multiplication and doing summation of the results and generating the unit value of this. In convolution for the image, it just keeps doing this until it generates a whole feature maps until it reaches the end. Now in CNN for images, you can have multiple kernels. So in this case, if I were to have 2 kernels in my convolution, it's trying to learn 2 separate feature maps. So in this case, the orange color is the feature maps of this. And then in the other dimension, it's trying to learn another feature maps, in this case, the red location. So in this case, it's going to have the output dimension of my feature maps with 2 kernels would be 2 by 5 by 5 tensor. Now, in the case of CNN for text, as we recall from last week's session, text is not the raw string of a text is not compatible with the neural network model. A neural network model is unable to understand the characters within the text. So what we have to do is convert that text into the word embedding, which is some vector representation of that specific word. So in this example right here, if we had the text, input text, how the CNN word, then it generates, let's say our word embedding is of 5 dimensions, then it will generate a matrix of 4 by 5. Now, the way CNN works in text is uh, very similar to image. However, um, we specify we only specify one dimension of the kernel. In this case, the kernel size is 2, and the remaining dimension of the kernel is the size of our word embedding. So we span across the whole word embedding. So in this case, we have a 2 by 5 kernel. And again, very similar to convolution, it does pairwise multiplication and summation just to get a scalar unit vector for these two words. So essentially in CNN, it's trying to do the space, the relationship in terms of temporal relationship. So the relationship, sequential relationship. So in this case, it's trying to find the relationship between, feature relationship between how and does through the word embeddings. Now, if on image CNNs, we perform strides both horizontally and vertically. However, in the word embedding, since it's only in one dimension, we only stride towards that one dimension, that sequential dimension. In this case, it's the sequence of words. So in this representation, our kernel actually slides one down, looking at the next pair of words. In this case, it's looking at does and CNN and doing the pairwise multiplication and summation to generate this scalar value for our feature maps. And again, finally, we reach the end, and we have a feature map for one kernel of 1 by 3. Now, if we were to add a second kernel, it would do the same thing. But appending the feature space in the other dimension. So we could do concatenation of this to generate just a matrix. So now R and N. Before I jump to R and N, are there any questions regarding CNN?
I have a question.
Yes.
I just want to ask, in the CNN, I understand when you reduce the dimension of the image and you have multiple layers.
So in terms of, right now I just have my input image is grayscale. So my input dimension is only one dimension for the input. Are you asking for when you have a colored image?
Oh, so there's difference with colored versus uncolored?
Yes. So with color, your kernel will be of dimension size of 1 by 2 by 2. Where if you were to have a colored image, if you specify the kernel size to be 2 by 2, it's actually 3 by 2 by 2 because it has to look at the dimensions of the red, blue, RGB, red, green, and blue
I see.
dimensions. Yes.
Okay. Well, what I was going to ask was, when you reduce the dimension quality, I guess in the colored version, RGB.
Yeah.
Is it, do you lose like any features from the image when you're putting it into the convolutional neural network because everything is being broken down, or is it still like every feature is maintained even if it's like a small, like a very small like features within that image?
Well, there is going to be some information that's going to be lost because what each kernel in your feature map is trying to highlight a specific feature. So if your feature map, if your kernel learned to identify vertical lines, for instance, let's say, when it does the overlap within your image and generates the feature map, it's really highlighting those vertical lines within your feature maps. So that's the idea with CNN when it comes to images, where the first layer of the CNN typically identifies low-level features such as lines, and then as you start moving towards deeper layers, it's identifying more refined more abstract features such as a circle, and then once you start moving up even farther in the network, you start identifying, let's say, a face, specific features. But each feature map is trying to identify a different feature, trying to learn a different feature.
Okay, I understand. Okay, thank
Yeah.
you.
Yeah. So there is going to be some loss. However, if you combine all those features together, then it should have enough representation to generate the output. Any other questions regarding CNN?
There's a question in a chat that
Yeah.
asks, would you mind explaining again about the convolution between textual data and the kernel?
Yeah. So the slight difference is in the image. So if we were to look at this image right here, right? This example right here where we have 4 words. When we convert these 4 words into the word embedding, we actually end up with a matrix of 4 by 5 if our word embedding was a 5 dimension. So we can kind of think of this as an image in the sense that, we can kind of think of this as a grayscale image where, again, it's an image is just really a matrix. However, when we're working with a convolution, we only really care about the representations, the features up and down. So the relationship between each word, where we actually don't look at the word embeddings separately. We combine all these word embeddings together. So this first row is representing the vector representation for how. This second one is doing the vector representation of does. So when we apply a kernel, let's say our kernel is 2, and we overlap it here at first, what it's trying to do is trying to find a feature map from the word embedding, such that a provenant feature map that provides a relationship between how and does. Then it strides over to the next pair of words. It tries to find a feature that's pertaining towards does and CNN. And then lastly, it does it for CNN and Word. So really, it's doing similar to image, the same way as image. However, when we do the stride, we're only striding in one direction. If I go back to our image, if you notice here, if we go from here to here, we stride one down, and we'll keep on striding until we reach all the way to the bottom. Then it actually goes back and tries to go to the next pixels that it did not see. So in terms of images, our stride, we specify it in 2 dimension. We say 2 by 2 or 3 by 3, 5 by 5. We commonly specify a kernel size of odd number, and the fact that when we have even numbers, the representation, the learned representation is skewed in terms of the reverse ordering. If you worked with image processing, you'll kind of see, if you play around with even numbers, you'll see some abnormalities with when the image is kind of flipped. So we kind of tend to leave with kernels of odd numbers when it comes to imaging. However, in the text realm, we only specify one dimension because the other dimension will always span the size of our word embedding. So if our word embedding in this case was only 3, our kernel size would be 2 by 3. And we only stride in the rows direction, in the directions of the pairing of the words, not in the dimension of the word embedding.
I have a quick question about the word embedding.
Yeah.
Would it be possible to have the letters as the embedded word? So in this case, we would have, let's say for English, 26 dimensions, where first dimension is representation of A, second dimension representation of B, and so on to Z. So and then we have to do 0 or 1, which says that if we have that specific letter or not. Would that be
So you can work on, there is different levels of granularity when it comes to word embeddings. Again, in this case, you could work at the character level. Oftentimes, though, if you're working at the character level of word embedding, it's most often that your output is trying to understand your output is trying to do some kind of classification on a whole word. For example, let's say our input is a single word and we want to determine if let's say our input is the characters of a word, and we want to determine if that word is spelled correctly or not spelled correctly. Or given a specific word, what is the correct spelling of it? An example like that. There's other things too, is you could work at looking at given a whole, for example, this whole, if I want to represent this whole document, how does CNN word? I could look at word embedding from the character level and embed the whole document using some aggregates of each character. I hope that clarifies it. So there are different levels of how you want to represent your specific input. So in this case, my input is a document, a whole sentence. I'm representing each word as it, but you can also look at each word separately and feeding that as an input. However, I can also take in the word embedding of each input and aggregate that result to generate one input, one word input, one sentence representation.
Okay,
So it'll kind of be like a sentence embedding.
Thank you.
Yeah. So that clarifies regarding the text. So now let's look at RNN. Very interesting architecture and the fact that it's a very powerful tool when you're working with data that's of its sequential order. There is some sequential properties regarding this, regarding your data. So just to recap from our deep learning session at session 2, we introduced feed-forward neural networks in that instance, where we had some input. It goes through some hidden layers and generates an output. So everything, the flow of data is in very one-directional. Now, with RNN, as the name suggests, not only do we have this input as well as some output, we actually have a loop back such that our the network output of the network gets fed back into it, as indicated by this looping arrow, where the output of this is going back as its input to predict help predict future outputs. Now, the thing with uh, recurring neural networks different from CNN, which is of the feed-forward nature. If we noticed in this instance, we fed in all our input at one time. However, for RNN, it's really, we treat each one as a separate time instance. So in this case, how does CNN, our first input of X would be how, and then does, then CNN, then were. So we feed it one at a time to RNN. So an interesting with recurring neural network, though, is if we unroll it, we actually see that the unrolled version of recurring neural network looks very similar to a feed-forward neural network, where everything is going in one direction. So the input, if we put in the first input and generate some output, and we take the second input and maintain the state from the prior instance and generate a next output, we can actually traverse through the gradients by unrolling it much easier. And we'll kind of see that through an example later on. So one thing regarding RNN, there's different types of RNNs that we can work with. One of them being a one-to-many RNN. So we have a single output and it's generating multiple outputs. So an example of applicability of this type of RNN is commonly in terms of a decoder. So if we wanted to, let's say, take an image and describe the image in text. So we would do a CNN encoder to encode a representation of the image, and that's that CNN, that encoding of the image will be our input to this RNN. And the output would be each word describing the content of that image. Now, another type of RNN is a many-to-one. So we have multiple inputs going into the RNN and only one output. Now, these type of application is actually what we have been focusing on in this workshop, which is specific to classification tasks. So this type of neural network is very good when it comes to classification, where we only want to generate one output based off the sequence of words. Now, another popular RNN is a many-to-many. In this case, I specifically distinguish this specific many-to-many in the fact that the number of inputs is equivalent to our number of outputs. So it has a the output and the input. The output and the input has a one-to-one mapping. So the first input will generate the first output. Second input will generate the second output, and the third input will generate the third output. An example of this type of RNN being used is if we were to do, let's say, name entity recognition, where we feed in the sentence, and for each word, we want to identify the name entity. If it's a name entity, or if it's, first of all, if it's a name entity or not a name entity, and if it is a name entity, of what type of name entity it is. So for example would be, if we cared about identifying locations, names, time, dates within the name entity, it will do those classification for each word. Now, another type of RNN, which is commonly used recently, which is very popular, is the many-to-many, where the number of inputs is not equivalent to the number of outputs. Now, the reason for the increase of this type of RNN gaining popularity is the fact that this type of RNN is primarily used in machine translation. Now, we'll have a look at some of the limitations to RNN. Now, I give this example uh, where we're trying to, similar to what we saw for language model, we're trying to predict what the next word is. Now, in this example, we have George is an Australian man who loves traditional fish and chips, but he has to wait until he goes back home too, and we have to try to predict this word. Now, as humans, it's very easy for us to predict what this next word is because we see the whole scope of this sentence, where the predicted word would be Australia, given the fact that George is an Australian man. So logic will tell us that his home would be Australia, would be a good candidate. Now, just to recap of how RNN works, so we have the forward pass, which based off the input, will feed in the input and try to generate a predicted output. And then we have the backward phase, which is which performs the actual learning component, where it calculates the error and calculates the derivatives to update the weights. So the way this works is, I didn't go into the mathematics of it, but essentially when you do backwards, during the backwards phase, after it calculates the error, when calculating the derivative, it tries to calculate the partial derivatives of the weights in relation to the error. And the mathematically, the way this forms out is we apply the chain rule that looks at calculating the partial derivative at each intermittent step. So in this example, if we were to try to find out how this RNN at the first instance affected the error of the output, it would try to calculate the relationship between the partial derivative between the instance of this one, this first RNN, to the output of this second RNN. And multiplied that by the partial derivative of how the model was how the output is affected. The partial derivative of the effect of how 3 was influenced by 2, and vice versa. And again, how at the end, it'll try to find out how y was affected by 3. So it's chain rule applied such that we do the calculation at each intermittent steps to find out the overall effect of how 1 influenced y by looking at how 2 was influenced by 1, how 3 was influenced by 2, and how 1 was influenced by 3, and multiplying those all together. So there is a question regarding the different nodes in a hidden layer. The 1, 2, and 3 are not representing different nodes in the hidden layer. It's all the same it's all the same nodes. It's all the same nodes. However, when you're calculating the outputs of these RNN, they're slightly different because one, the input is different, as well as the initial state that it's starting off is different. So the effect of the weights here is influenced by what happened here because of the initial input. So they're the same nodes. However, um, because the inputs are different, they're having different influence at different times. So now the reason why this is important in the fact that where that chain rule is important in the realm of RNN. If we were to look at our example again, and we know that Australia, the output Australia is highly dependent on the input Australian, which occurred 19 connections prior to it. That's a very long sequence of partial derivatives that it has to calculate. So if our partial derivatives are, the gradients of those partial derivatives are all below 1, when we calculate the influence between the, the weights of Rnn given this input to the output, will be significantly low, meaning that the weights of our Rnn will not be updated significantly based off our input Australian. The reason why that is because, as you recall, as we multiply values less than 1, we significantly get lower and lower numbers. So when this occurs, this is what we call the vanishing gradients, where our gradient becomes very small, such that our model is unable to learn. So this is where Lstm comes in and tries to mitigate that problem with the vanishing gradients as well as exploding gradients, where if our value, our partial derivatives between each point is above 1, then we'll have a tendency for that gradient to explode. So right here, I currently have depicted is the architecture of a simple RNN, where given our new information coming in, we have some type of networks that perform some activation, commonly sigmoid, let's say, and generates the output and loops back in. So this is the depiction of our regular RNN. Now we're going to modify this such that we build towards the LSTM model to mitigate that vanishing and exploding gradient problem by introducing some form of memory. So the very first thing we want to do is have another subnetworks to try to learn what information needs to be forgotten within our memory. So if we actually go back to our example here, as we progress through each word as input, it's trying to forget certain aspects of information that it already learned. Slowly by slowly, what it's trying to do is, given this input, so if we were to get the input who, and we've already saw George is an Australian man, during this instance, it tries to identify what information is not as useful. So that's what the forget does. It's a network that has an activation of uh, sorry, that has an activation of sigmoid, so that our values go from 0 to 1, so that when we do multiplication of the memory, pairwise multiplication of our prior memory states, it's trying to forget specific information because, again, it's pushing certain values towards 0 and certain values towards 1. So 1, we're trying to maintain that information. 0, we're trying to forget that information. Now, we have this other notion of the information, the new information that we get in. We want to update our memory. However, there's specific information that we not necessarily find important. This is where this next subnetwork comes in, where we have a network that we call it the ignoring network, that again is of a sigmoid activation function, so that the outputs of this will push the values towards 0 or 1, providing us the mechanisms to uh, to ignore specific information from the specific new information coming in, and maintaining some that's important to us. Now, the last component with the Lstm is from our memory. What we want to do is try to understand what information we want to select from it in order to provide our prediction. This is where this network comes in. Again, we have the sigmoid activation function, and we want to push those values again towards 0 to 1 to determine, so that when we get our collected possible outputs, we're only selecting the ones that's important to us. Are there any questions regarding Lstm? Okay, so if there's no questions regarding um, Lstm, what I suggest is we can take, let's say, 10-minute break if everybody's okay. And then we can reconvene at 7 o'clock for the application component. So I hope everybody is back now. If there's no objections, I'll go ahead and begin with the coding component of the session. So in this week's session, we'll be looking at a slightly different data set. We'll be looking at the Quora question pairs. So this comes again from the Kaggle. And what this data set consists of is a set of questionnaires from users through the Quora platform. And what it tries to do is tries to determine if two questions are semantically the same. So if they have the same meaning or not. And it It's just a simple binary classification that's trying to, if they are the same, then they're identified as duplicate. If they're not the same, then they're identified as not being duplicate. So our data sets, if we look at Kaggle, actually provides us as a CSV file, where the first row is the ID of the specific record, the ID of question 1, ID of question 2, actually question 1, actual text, full text of question 2, and our actual true labels of is duplicate, where 1 is representing yes and 0 is representing no. So if we look at the code, let me zoom in. So in this first file, what we're going to do is do some initial pre-processing that we've learned in prior session. So in this specific line of code, this should be very familiar in the fact that we do the mounting as well as we download the data set from Kaggle and save it into our drive. Specific line of code, what we'll be doing is generating, we're doing the mounting. So in case you already have the data already installed, unzipped, and unzipped, then we just need to do the mounting. Then we do some necessary importations of important libraries. And then this specific line of code, what we're doing is loading in the data, determining, just getting an idea of its dimensions, as well as dropping out any null entries. So if we see, after all that, we have no null values. And if we examine the data sets, we see very similar to what we saw in Kaggle, where we have the ID of the actual data point, we have the ID of question 1, we have ID of question 2, and then the actual label, the actual text for each question, as well as the true label. This step will do some initial definition of some pre-processing, again using spaCy similar to prior session. And we are just going to do stemming. And then in this instance, we want to clean up the question 1, as well as clean up question 2. So again, this is going to take quite a while. Let's see. This should take a few minutes. So while we wait for that to load, let's just go ahead and review the other components. Now, what we want to do is we want to make sure we also do drop any null values again, just in case during our pre-processing, if, for instance, we had some where our text was all numbers that really wasn't cleaned to be wasn't initially clean to begin with, that our process would have our pre-process would have cleaned that component out. So we want to go ahead and remove those entries as well. And in this case, what I'm doing is I'm just dropping out the unpreprocessed columns and just maintaining the preprocessed columns. In this line of code, I just want to save our preprocessed data. So if I'm doing some additional work here where I'm going to manipulate just the preprocessed data, I don't need to do the preprocessing again. I can just load in that save, the cleaned up version. So once this is done, let's see if I can stop it. And load in the data that I've saved initially. So we have the cleaned version where we have everything in lowercase. It's stamped, as well as we remove non-alpha characters. Now, what we're going to do is we're actually going to use a pre-trained word-to-vec model in our neural network. So what we're going to do is similar to what we did last week. We're actually going to use word-to-vec to generate our vocabulary and initially train our word embedding using word2vec. So let me actually stop that as well. So this is very similar to last week. What we're doing is just generating phrases for each of the sentences, performing the necessary imports, defining our word2vec model. In this case, we're looking at a model with the frequencies of minimum frequency of 5 for each word in our vocabulary. Our window size for our word2vec is 5. We're trying to generate a word embedding of a dimension size of 200. We specify our sampling rate, our alpha, as well as minimum alpha and sampling, as well as number of workers we're going to use for a course. In this case, again, this is building up our vocabulary. It's building up vocabulary. Now, this is slightly different that we did not do in prior sessions. Now, since we're using a pre-trained word2vec in our network that we'll see, we need to actually correlate our text to be some form of ID. So what we're going to do is provide a unique ID to each word using the vocabulary. So again, I'm just going to start off my unique ID with a value of 1. And I'm going through the vocabulary list and generating a mapping from the token word to its ID. And then in reverse, I want to have a mapping for the ID back to its original word. This section actually generates our modeling. Sorry, this is actually this block of code performs our training. And once we're trained, we can just get our word vectors. And again, so we don't need to rerun that process in future. We can save all those results. And I'm going to go ahead and load in. Load in our IDs. Now for the pre-processing stage, we want to, just to make it a little bit easier for ourselves, what I'm going to do is convert all our words into its associated ID. So that's what this process is defining, this pre-process. We're just looking at each word and converting it to the ID. This is the line of code that actually performs that. And we see that we have the clean version and we have its representation in terms of its ID of each word. Again, we can save those results. And this is our pre-processed data where we're just looking at the IDs. Now, one thing we want to do in preparation for our network is generate the word embedding matrix for our embedding layer for our neural network. So the way we do that is we use NumPy. We specify our dimension size, and we specify our vocabulary size to be of this dimension, +1. We add the +1 because we're actually going to add padding in our embedding layer. And this is, shouldn't actually be here. This is, can remove that. And then we can load in our word-to-vec model, the word vectors that we learned through by training our model. When we trained our model. And in this step, all we're doing is generating a matrix for our weights where it's of the dimension of the vocabulary size with the number of embeddings. Then we iterate through our token IDs and populate each row with its associated. So each row in the matrix is represented by its specific word ID. So the word with ID 1 will be within the weights for that word would be in row 1 of the weighted matrix. So all we have to do is populate, get the word vector from our GenSub model and populate and transfer it over. And we're going to go ahead and save that. We forgot to run this. I think I forgot to load in token to ID. I think we have it. So it's not recognizing the token to ID. However, we do have it created. Okay, let me just reload it in this cell. Why isn't it not? I think I might have accidentally deleted it. I will. So I can't run this at the moment because I think I accidentally deleted the token to ID in my Google Drive. However, I'll upload the token to ID on the GitHub repository as well. Oh, I think someone identified. Yes, you are right. It's Cap. Thank you, Ernest. There we go. So, minor syntax error. So what this does is generates our pre-trained NumPy matrix and saves it as a NumPy matrix. Now, if we look at our LSTM model, what we can do is go ahead and mount our necessary imports. We'll go ahead and load in our trained preprocessed data already. This is the imports of the torch. What we do here is just split up the data set from training to validation, where training will contain 80% of the original training data sets and val will contain 20%. And we see that they're all same dimensions. Now, to define the model, what we're doing is just using one LSTM to process the whole, to process question 1 and question 2 to find out a latent representation for each sentences. And then we will feed those latent representations to a multi-layer classification layer that just generate with a sigmoid activation to generate binary classification output. So this is the definition of that model. What we pass in is actually our pre-trained embedding layer. From the pre-trained embedding matrix, we calculate the vocab size as well as the embedding dimension. We go ahead and, sorry, this should actually be first command. That, as well as we can define the number of layers we have in our LSTM model. Now, in the embedding layer, what we do is we create an embedding layer. We specify the vocab size and the embedding dimension, as well as a padding index, which we will use 0 as our padding. And then we specify for the sparse, we specify false because we don't want to, our input is not of a sparse matrix. And then we load in our pre-trained weights using the load state dictionary command. And we specifically load in the weights, taking our pre-trained model and converting it to a tensor. Now for the LSTM, we just need to specify the input size. In this case, the input size would be the dimension of our embedding layer. And then we would specify our hidden size. The hidden size is typically the same dimensions as the input size. However, you can adjust that as well to be different. And we specify batch first to equal true, just to maintain the uniformity structure of our tensors. So the output of the LSTM, the first dimension of our tensor will be the batch, will represent the batch. And then we have the multi-layer classification layer, which is just a multi-layer, which is just fully connected hidden layer with number of the input size being the embedding dimension times 2. The reason why we specify multiply is the fact that we're using the same LSTM to generate latent representation for question 1 and question 2. And the number of neurons in this classification is just 1 because we're just doing a binary classification problem. Now, in the feed forward component, we feed in our question 1. Since the length of our sentences may differ, we actually use a padded sequence to take care of the variable length sentences. Then that's what the padded sequence does. It takes in the input of the embedding, as well as we need to know the length of each sentence. And then you need to specify enforce sorted if the input, if your input is not sorted. So if the length of your sentences are not sorted in ascending order. And then finally, we pass it into the LSTM to generate the output as well as the states of that. We do the same thing for question 2. Take the outputs of the LSTM both from question 1 and question 2. So we get the latent representation for question 1 and question 2. Concatenate them together and feed it to our classification. And of course, apply the sigmoid activation function. This is the components of very similar to what we saw in session 2, trying to determine if GPU is available or not. In this line of code, we're just going to load in our pre-trained NumPy weights. And here, what we're going to do is actually build our model, move it to the proper device. So if our GPU, if we have GPU capability, we're going to move it to the GPU. Specify the optimizer, the loss function, and number of epochs. Now, for our data sets, to define our data, since our data set, we nicely process it in Pandas in the prior notebook, we can just pass in the actual data frame, Pandas data frame. Define how to get the length, which is simple since it's we can just use the shape from the data frame. And to actually retrieve each data points in our data sets, we just go through and select the specific row in the data frame based off the ID. And then we'll go ahead and create a dictionary with our Q1, Q2, and our label, and converting those information as a NumPy. Now, this is an important function. This is really defining for our data loader how to formulate our batch, And what we're doing here is just taking all the elements, taking all the information from our data points and consolidating it together based off the key. So we will create a dictionary where Q1 contains all questions from each data point, and Q2 will have a dictionary for Q2, which will contain questions 2 for each data point and each label for each data point. And then since in our pad sequence, when we did the padding, when we packed our pad sequences, we need to understand the lengths. We actually do that in the pad collate function to calculate the length of each sentence for question 1 and question 2 for all the data points in our batch. And then before we do anything, we actually pad our we pad all our sentences with a 0 value and return our padded value as well as our lengths and our labels. I provided the starting positions of defining the data loader, and I think it would be a good exercise to kind of test your knowledge, prior knowledge of specifically session 2 and implementing the training components of it. The remaining coding for implementing the training will be very similar to that of session 2. That would wrap up the end of the coding component. Is there any questions? So if there's no other questions, I'll go ahead and update the GitHub repository. Will this code be available on GitHub for reference? I think it should already be available there, but I need to update it based off the minor change that I made. Let me double check that it's already up there. Oh, I see that I haven't updated yet. So I will push it to the GitHub repository, make it visible to everybody after this session. So you should have it for reference. Any other questions? Okay, if there's no other questions, next week's sessions, I have prepared the next talk for the section for bidirectional transformers. Now, I was reviewing what I had prepared for the bidirectional transformers. I think it's a very interesting topic. However, I think there's also another interesting topic that can be covered when it comes to uh, NLP, specifically LSTM, which I don't cover in bidirectional, is attention mechanism. Similar to what we did in the last session, if everybody can use the raise hand component, I just want to get an understanding of who would be interested in the next session to incorporate attention. The caveat is, though, is attention and bidirectional transformers are large topics on their own. So if I were to include it, it wouldn't go as depth. Let me see. So I just wanted to know who would be interested in incorporating attention, or primarily looking at uh, who's interested in incorporating, looking at understanding attention mechanisms at the next session.
Alex, would you be able to give just a very quick what, information about how these two are different?
So the thing though, so bidirectional transformers is the type of uh, architecture that it uses the concept of attention. So attention is this mechanism that tries to identify what area to focus on. So in LSTM that we've seen, in most cases without attention, what it has a problem of is that it treats all the inputs that it saw thus far equally, with equal weights. Now with attention mechanism, what it does is, as we provide input, so let me actually bring up this one of the slides again of RNN. And so if you notice an example, the one-to-many, without attention, what it's doing is it's looking at generating the output based off the hidden state of the final RNN. So it's actually treating the inputs, the weights of each input equally. Now, with attention mechanism, what it's going to do is try to understand which input it needs to pay attention, which input it needs to pay more attention to generate the proper output. Now, with bidirectional transformers, um, it applies attention mechanisms, but it uses this notion of self-attention, that it tries to find attention within itself. So initially, what I have it as is a brief run through of attention, the attention, and kind of glancing at it. But I just wanted to get an understanding if people want more in depth on the attention mechanism, specifically how you would apply attention mechanism programmatically through a simple LSTM. So we have a couple. To make it easier, instead of typing it in, just so I can see a quick glance of if it's majority of people, do you mind if anybody that's interested, use the raise hand component in the participation? Okay. So we have some interested parties. What I will do then is similar to CNN. I'll cover it. I'll cover it within the slides, and then skip over it in the coding component of it. Okay. So I think that's the end of this session. Do you have any closing comments, Eunice?
No, thank you so much for the great
Okay.
talk again. So as
Okay.
always, I will share the slides as well as the video recording for this week with everyone.
Okay. Thank you. And I shall upload. You should have the code available for reference as well in GitHub
Great.
program. Okay. Thank you.
Great. Thank you, everyone, and hope you all have a good week. Bye.